Hello everyone, this is Shiv Prakash. This video explores the significance of most oftenly ignored parameters in boost converter. Let's find out how. This is the circuit diagram of ideal boost converter. Ideal boost converter means zero internal resistance of inductor, capacitor, zero switching losses, and zero diodic resistance. The ratio of output voltage to the input voltage is given by 1 upon 1 minus D, where D is the ratio of T on and the sum of T on plus T off. Here, T on is on time of the switch and T off is the off time of the switch. If we analyze the transfer ratio at the endpoints of D, that is 0 and 1, we can point out the problem with this ratio. At D equals 0, V0 is equal to VDC. That looks fine. At D equals 1, V0 equals infinity, which is not at all feasible. We will plot this in MATLAB and verify the results in the next slide. In this slide, we can see that on the right hand side, the MATLAB code is displayed, and on the left hand side, the corresponding graph is displayed. So the graph is between duty ratio and the output voltage V0 in volts. If you can see here, at the duty ratio 0, the output voltage is near to 100. As we can see, the scale of the y-axis is 10 raised to the power 4, therefore we are not able to see that input voltage is equal to 100 volts that is being used in the code. At the end point, the duty ratio equals 1, we can see that the output voltage approaches near to the infinity. So by this graph, we can identify and verify the results we got in the previous slide. This is the circuit diagram of boost converter, which contains the internal resistance of the inductor in the circuit. The voltage ratio V0 by VDC is given by this equation. If we substitute R equal to 0, we will reach to the condition of the voltage transfer ratio for the ideal boost converter. As we can see here, only the internal resistance of the inductor is being considered. Again, we can also consider different losses, switching losses, as well as the capacitor internal resistance, but for the simplicity of the expression, we are just considering the internal resistance of the inductor. In the next slide, we will see the verification of this equation. In this slide, we can see that on the right hand side, the MATLAB code is there for representing the above equation for the voltage transfer ratio, and on the left hand side the corresponding graph is there. If we see the corresponding graph, we can clearly identify that when the duty ratio is 0, the output voltage is just a finite voltage when D is 0, and when the D is 1, that means the switch is permanently on, the output voltage is 0. Also we can see that in between these two extreme conditions, the voltage reaches a maximum, that is at 0.7 duty ratio. After this video, I am going to derive how these steady state voltage equations came in and how can we consider different approximations. Also, we will derive these steady state voltage transfer ratio by using state space averaging method in the next video. Thank you.